We will begin the presentation of CSEC Multiple Choice Practice Paper 5 with Part A. Part A will consist of the first 15 problems in the entire CSEC Practice Paper 5. This problem requires that we find the sum of two squares. It is important also to note that the squares are actually squares of negative numbers. The only problem that candidates may have that might prevent them from arriving at the correct answer is forgetting that the square of a negative number is positive. Some may even go as far as interpreting the square of a number as multiplying the number by 2. We will square each number by multiplying it by itself, and at the same time be aware that the square of a negative number is positive. Square negative 3 and the answer is positive 9. Square negative 2 and the answer is positive 4. Nine plus 4 is equal to 13. The correct answer is option C. When squaring a number, we multiply it by itself. Squaring negative 3, we have right there negative 3 squared. That is equal to negative 3 multiplied by negative 3. According to the rules that we use to manipulate directed numbers, negative multiplied by negative is equal to positive. The answer is positive 9. We are multiplying negative 3 by negative 3. Negative multiplied by negative is equal to positive. The answer is positive 9. With or without the positive sign, the number is still positive. So we may write a positive number without the positive sign. It is still positive. Next, we have 11.1 divided by 0.01. We may take any of a few approaches to the solution of this problem. However, the one that I will opt for is to consider that 0.01 is equal to 1 over 100 or 1 divided by 100. Dividing a number by a fraction is the same as multiplying by the reciprocal of that fraction. Another name for reciprocal is multiplicative inverse. So instead of writing divide by, we have written multiplied by, but we have reciprocated the fraction. Dividing a number by 1 results in the same number as we have it right here. Therefore, we are multiplying 11.1 by 100. Multiplying a number by 100 increases its value by 2 places of decimal. There is only one place of decimal. An additional 0 will be included. So we have this number to be increased by 2 places of decimal But as it is right here, we have only one place of decimal. To increase this number by 2 places of decimal, we will include an additional 0. The answer is 1110. The correct answer is option D. We may consider that a number that has a decimal fraction has a reservoir of possible zeros that may be placed to the right of the rightmost non-zero digit without changing the value of the number. In this particular case, we need only one of those numbers. So we can consider that because we have 11.1, we may place a lot of zeros behind or to the right of this one without actually changing the value of the number. We are calling those trailing zeros that do not affect the value of that number. In this particular case, because we are increasing by 2 places of decimal, we only need one of those zeros to be applied. Then we will now increase by 2 places of decimal. Increasing by 2 places of decimal makes a lot more sense in this particular case. So if we consider that the number will have a reservoir of possible zeros that may be placed to the right of the rightmost non-zero digit in the decimal fraction that we are talking about, then we may apply an extra 0 without affecting the value of the number. Multiplying by 100, which is increasing by 2 places of decimal, may, in this particular case, make a bit more sense. The number 3076 written in standard form is, when writing a number in standard form, it is increased or decreased by the number of decimal places required for it to have one non-zero digit to the left of the decimal point. The number in question has no decimal point. The decimal point is considered to be at its extreme right, like so. In this particular case, count the number of decimal places that the number will be reduced by, because we are going to decrease by a particular number of decimal places in order that we can have only one non-zero digit to the left of the decimal point. So we haven't moved as yet. This is our first movement. 1, 2, 3. The number is reduced by 3 places of decimal. The number is therefore divided by 10 to the power of 3. We need to recover the original value of the number by multiplying by 10 to the positive 3. So in reducing the number by 3 places of decimal, we have divided the number by 10 to the power of 3. In order to recover the original value of the number, we need to multiply it by 10 to the positive 3. We need to understand that writing a number in standard form is, as it says, writing the number in a different form. Writing the number in that different form or that other form does not change the value of the number, or should not change the value of the number. So if we divide by 3 in order that we may comply with the form, in order that we can recover the original value of the number, we need to multiply by 10 to the power of 3. The correct answer is option A. In arriving at the form that is required, the number may be increased or decreased by a particular number of decimal places. Where a decrease was necessary, the power of 10 used must demonstrate that the number is being increased back to its original value. We would expect the reverse process for a number that had to be increased, because in writing a number in standard form, it may be that the number will have to be increased by a particular number of decimal places. In that event, to recover the original value, we will have to divide by the power of 10 that was necessary, and in that event, the power of 10 that we multiply by will turn out to be negative. If $560 is shared in the ratio 2 to 3 to 9, the difference between the largest and the smallest share is what we need to determine. As I always say, it is possible that 2 may take a longer time than 5. It is better to take an extra 5 seconds thinking about a problem rather than an extra 2 minutes to work it out. We have 3 shares. However, the total number of units is 14, so we have 14 units. Adding the number of units in each share, we have 14 units. The one with the smallest share received 2 out of 14, and the one with the largest received 9 out of 14. So we have 2 out of 14 to be multiplied by the amount shared, 9 out of 14 to be multiplied by the amount shared. Each fraction may be reduced by a common factor of 14. We have 560 divided by 14 is 40. So in this case we will have 40 to be multiplied by 2, and here we have 40 to be multiplied by 9. One results in $80 and the other results in $360. Find the difference between the two results. As it is said, the difference between the largest and the smallest share. The correct answer is option C, $280. On second thought, we could have subtracted the numbers in the ratio that represented the largest and the smallest share. It is said the difference between the largest and the smallest share. So we have 9, we have 2. We subtract 2 from 9. The result is 7. We may use it in calculating the difference between the two shares. The difference between the two shares, 9 minus 2 is equal to 7. And we know it is 7 out of 14. 7 is half of 14. The portion will be half of 560, and that will give us 280. What I meant by the 2 taking a lot more time or a longer time than the 5 is this. Remember that when we were calculating the two different shares here, we did not use the total time. Because of this technology, we we're calculating the two of them the same time. So it took a lot shorter time than if we had to do this one and then do this one, as opposed to just subtracting 9 minus 2 is equal to 7. 7 is half of 14. So we are talking about half of the amount of the total that was shared. And if we took just another 5 seconds to look at the problem, we may have taken 2 minutes shorter in solving it. In a school, the ratio of the number of pupils to the number of teachers is 20 to 1. If the number of pupils is 840, how many teachers are there? One of the number in the ratio is 1. This greatly simplifies our work. The problem boils down to a matter of multiplying or dividing by 20. Because one of these numbers in the ratio is 1, as we can see, we know that we cannot possibly have anything difficult to do. All we need to do is to determine if we need to multiply by 840, which is multiplying 840 by 20, or divide 840 by 20. If we wanted to be realistic, we may go straight ahead and divide the number of pupils by 20. Realistic means we imagine that we will have less teachers than students, so we'll just divide by 20. And not considering any mathematical principle, just being realistic, we just take that approach, dividing by 20. The result turns out to be 42. The number of teachers is 42, and this is represented by option B. Some candidates may be undone by the ease with which we arrived at the answer. Their greatest problem will be that they find it impossible to believe that the calculation should be so simple. Right. Generally, when I give my students an extra easy problem, they find it so unbelievable that very few of them are able to solve it. And I always tell them, I am going to pray that you get a very difficult examination, because when the problem is difficult, you'll know exactly what to do. But you have difficulty solving very simple problems. Let us therefore set up a nice ratio problem with the number of pupils on the one hand and the number of teachers on the other. So there we have our ratio problem: pupils, teachers. The number of pupils to the number of teachers. The ratio is 20 to 1. How do we know that the 20 shouldn't be on this side and the 1 on the other side? Because we are including the numbers here respectively. So we have in a school the ratio of the number of pupils to the number of teachers. So the number of pupils will go first, the number of teachers will go second, and we have it right here. Therefore, any calculation that we are about to make, we must know beforehand that whatever we get for the number of teachers must be smaller than the number of pupils, according to the order in which we have these numbers right here. On the pupil side, the number is larger than the number that we have on the teacher's side. We know the number of pupils to be 840, but we do not know the number of teachers, and we are going to call that X. Right. So everything is consistent. Pupils, teachers. according to the information of the problem? Pupils to teachers. Pupils go first, teachers go second, and we have it all in order right here. According to the numbers that we have in the ratio, we may say 840 over 20 is equal to x over 1. 840 over 20 is equal to x over 1. Like so. There we have it. X will still be 840 divided by 20 as we had before. Being realistic, we do not imagine that under normal conditions there should be 20 times as many teachers in a school as pupils. However, I'm a little bit alarmed of what the distractions could be in some of the other options that were given. There are 40 students in a class. Girls make up 60% of the class. 20% of the girls wear glasses. How many girls in the class wear glasses? 40 students. There are 40 students in the entire class. There we have 40. Girls make up 60% of the class. That means of the total number in the class, 40, then 60% of those is girls. Girls make up 60% of the class. To find the number of girls, we multiply the number in the class by 60%, which is 60 over 100, or 60 divided by 100. So 60% will be girls. So 60% of 40, that will give us the number of girls. And of the number of girls, 25% of them wear glasses. 25% of the girls wear glasses. We will therefore multiply by a further 25%, and that is 25 over 100. 40 students in all. 60% of those students are girls. Then we know that all of these are girls. Of the number of girls, 25% of them wear glasses. So we multiply by a further 25%, and we will have a lot of fun with these figures. We may reduce the fractions by a common factor of 100 by striking two zeros from both numerator and denominator. That is how we do it in primary school. Cross off two zeros there means that we are reducing by 100, or a factor of 100. Then we cross off two zeros here also, meaning that we are reducing by a factor of 100. And what do we know? Investigating the remaining numbers, we may be able to see that in the numerator, 4 multiplied by 25 is equal to 100. And there is another 100 in the denominator. Those will eliminate each other. The only remaining number is 6. So 25 multiplied by 4, 100. And there we have another 100. Those will eliminate each other. The only number that will be left is 6. Right. The correct answer is option A. Be always on the lookout for numbers that may turn out to be easy to manipulate. Examiners will quite infrequently set problems with numbers that are hard to manipulate or that will give outrageous answers. By the distributive law, 49 multiplied by 17 plus 3 multiplied by 49 will be which one of these? The distributive law states that multiplication is distributive over addition. This means that if we have a sum to be multiplied by a given number, that number may be distributed to each number in the sum. We are using this as an example where we have a sum 3 plus 4 plus 6, and that sum is to be multiplied by 5. The number 5 is preceding the bracket with no arithmetic operator separating it from the bracket. Means that we are multiplying the contents of the bracket by 5. Five may therefore be distributed to each of, or if we prefer, among all of the numbers in the bracket. So we have this 5 distributed to all of these, and this is how we do it. 5 multiplied by 3, then 5 multiplied by 4, and 5 multiplied by 6. 5 multiplied by 3 will be added to 5 multiplied by 4, and that will be added to 5 multiplied by 6. There we see the 5 is common in all terms. It is the one that was distributed. In the statement of the problem, the 49 is common. It is the one that was distributed. It needs to take its place in front of the bracket, and the sum of the others will be inside of the brackets. So the one that was distributed will be present in all of the terms. We have right here that 49 is present in the two terms. That means it is the one that was distributed. The 5 that was distributed in all terms is multiplied by the contents of the bracket. Therefore, we imagine that 49, the one that was distributed, the one that was present, or the one that is present in all of the terms, will take its place in front of the brackets, and the others will be added inside of the brackets just as we have them right here. So 17 and 3 will be added inside of the bracket. Preceding the brackets without any operation means multiplication, and the numbers inside of the brackets will be added. 49, we don't have a sign here, means that we are multiplying 49 by the contents of the brackets, and the contents will be 17 plus 3, which is equal to 20. So it is 49 multiplied by 20. The correct answer is option D. A student used a rod to measure the distance 3.6 meters, 5.4 meters, and 7.2 meters. What was the greatest length of the rod if it fitted each distance an exact number of times? The greatest distractor in this problem may not be among the options, but in the statement of the problem. Students generally hate fractions, especially vulgar fractions. Decimal fractions, they are not affected by them except when they have to manipulate them without using calculators, like in multiple choice exams. This same situation that we have right here. The examiners have made the decimal fraction simple by causing each of them to have the same number of decimal places. In manipulating them, we may neglect the decimal place, then reintroduce it in our answer. So the decimal places are there, and some students are panicking. However, the examiners use the same number of decimal place in order that we can have some uniformity. This reduces the difficulty with which the problem may be solved. We may therefore treat this situation as if we have 36, 54, and 72. Then we reintroduce a single place of decimal in the answer. What about that word? The word greatest need no extra highlight and serves as a great clue, giving away the question. From this, we may correctly conclude that the answer will be the highest common factor of the numbers involved. Because we know that HCF does not have decimal places, we may be a little out of our depth. If we use 36, 54, and 72, it is easy to see that the HCF of those numbers is 18. Some candidates may just be able to look at 36, 54, and 72 and determine just by looking at them that the highest common factor is 18. No problem seeing that 1.8 is the correct answer. Reapplying the decimal place to the answer, we see that the correct answer is 1.8 meters. This is represented by option B. Some candidates will very readily see the HCF of the numbers, but some others may need to do a little calculation. Let us use this first method to calculate the HCF. First method of calculating the HCF, we may easily find all of the factors of the numbers by making use of a table. Divide each number by the first common prime factor, then attempt to do the same with the results until no further division can take place. This may be a great mouthful, and of itself the statement very difficult. Not necessarily very difficult, but we may say not easily understood. But the demonstration that we will put forward in a few seconds will help to clarify. We are attempting to find the highest common factor. So what do? All the numbers are included in a table. We find the first factor that is common using, as we do generally in primary school, selecting the smallest prime factor and see if it is able to divide into 36, 54, and 72. Now we are looking for the highest common factor. We need the common factors of 36, 54, and 72. Use the smallest prime number that is common to all of the numbers, and that common prime factor is 2. So 2 will be the one that we will begin with. 2 is common to all. We are searching for the highest common factor. We can only use factors that are common to all. So we have 36 divided by 2 is 18, 54 divided by 2 is 27, and 72 divided by 2 is 36. Then what do? 3 is the next factor common to all. We are only using the factors that are common to all. The other one that is common to all is 3. We will use that one. Then 18 divided by 3 is 6, 27 divided by 3 is 9, and 36 divided by 3 is 12. 6, 9, 12. If there is any other common factor, we may use that common factor again. And we see that 6, 9, 12 has a common factor of 3. So we may use 3 again. 6 divided by 3 is 2, 9 divided by 3 is 3, and 12 divided by 3 is 4. The HCF is the product of the common prime factors. The HCF is 2 multiplied by 3 multiplied by 3, and that is equal to 18. And of course we need to reapply the single place of decimal, and the result will be 1.8. But why didn't we move on from this point? Because 2, 3, and 4 do not all have a common factor, with the exception of 1, and 1 will not affect a product. There is no common factor, so that is where our repeated division ends. Same problem. Let us find the HCF of the numbers by using another method. This time we will write down all of the factors of the three numbers and select the largest one that is common to all of them. Factors of 36 are those numbers that can divide into 36 without leaving a remainder. Let us write down all of the factors of 36. There we have them. All the numbers that can divide into 36 without leaving a remainder. Factors of 54 are those numbers that can divide into 54 without leaving a remainder. Let us write down all of the factors of 54. And there we have them. Factors of 72 are numbers that can divide into 72 without leaving a remainder. Let us write down all of the factors of 72. The largest number present in all three sets is 18. Reintroducing the one place of decimal makes 1.8 meters. The correct answer as we have determined on the previous occasion. So we have all of the factors of 54, of 36, of 72. We can take a check and see which number is the largest one that is present in the three sets. Hence, that will be the highest common factor, the largest one that is common to all. At the end, we may reintroduce the single place of decimal, and the answer is 1.8. $301 can be written as any number written in the form suggested by the options is in exponential form. In exponential form, the power of 10 tells us the number of zeros that are intended. Exponential form. That's what we have here. So we have 10 to the power of 3. So we have 1 followed by 3 zeros. We have 10 to the power of 2 followed by 2 zeros. We have 10 to the power of 1. We have 10 to the power of 1. 1 followed by 1 0. And if we have 10 to the power of 0, then we will have 1 followed by no 0. And that will be 1. Any number raised to the power of 0 is equal to 1. And this applies to 10 also. As a matter of fact, the 0 power tells us there is no 0, as we discussed before. So we will write down 301. Big and bold. Write down the place values. Place values are hundreds, tens, and ones. We love those from primary school. Replace the regular place values with their exponential form. So hundreds will be 10 to the power of 2 and so on, but we are beginning with the first place value of ones, that will be 10 to the power of 0. Then we have 10 to the power of 1. Then we have 10 to the power of 2. The answer may now be written in exponential form, meaning that 1 is 3 multiplied by 10 to the power of 2, or 10 squared. Then we add 0 multiplied by 10 to the power of 1. And we finish up by adding 1 multiplied by 10 to the power of 0. Although our answer is correct, the options dictate that we eliminate the term with 0, and also consider that 10 to the power of 0 is equal to 1. Therefore, by just considering what we have in the options, that we do not have a term in here that is reflective of this one, and at the end we have plus 1 plus 1, then what do? We eliminate that term, this one in the middle, and what do? Take a look at this. Good. So we have that expression that we had before, which is that one, and we see that it is equivalent to 3 multiplied by 10 squared, or 10 to the power of 2, plus 1. The correct answer is option D. A half raised to the power of 3, that is preceded by a negative sign. So a half raised to the power of 3 preceded by a negative sign, that may be read negative a half cubed, and we need to determine what that negative a half cubed is the same thing as. We have a negative sign right there that we need to take note of. Notice that the negative sign is outside of the brackets. This means that the brackets need to be worked out, then the sign is to be applied to the result. We need to first find the cube of a half. The cube of any number is found by multiplying 3 occurrences of that number together. A half cubed is equal to a half multiplied by a half multiplied by a half. 3 occurrences of a half multiplied together. The product of all of the numerators is 1, and the product of all of the denominators is 8. So the result is 1/8. Multiplying all of these, 1 multiplied by 1 multiplied by 1 is 1. 2 multiplied by 2 is 4. Then multiplied by 2 again. 4 multiplied by 2 is equal to 8. Do not forget that the negative sign is to be applied to the final result. There we have the negative being applied to the final result. The answer is option A, -1/8. On seeing the power and the negative sign, some candidates may be considering situations like the square of a negative, the negative of a square, the cube of a negative, the negative of a cube, etc. We will take a look at them. We will consider them right here. The square of a negative is positive. As a matter of fact, the square of any number is positive. Squaring a number requires that the number is multiplied by itself. 4 squared is equal to 4 multiplied by 4. And that is equal to 16. If the number is negative, then we know that a negative multiplied by negative results in a positive. So we have right there negative 4 squared is equal to negative 4 multiplied by negative 4. Negative multiplied by negative is positive. The result is positive 16. We have already concluded that the square of any number, positive or negative, must be positive. The negative of a square is simply applying a negative sign to any number that is already squared. The result must therefore always be negative, since we are simply applying a negative sign to a positive number. Therefore, the negative of a square is always negative, because a square has to be positive. Therefore, we are only applying a negative sign to a number that is already positive. So we say that negative of 4 squared is negative of 4 multiplied by 4. 4 multiplied by 4 is 16. And we have the negative sign right there applying. No harm in that. Also, if we have the negative of the square of a negative, as we have right here, we are squaring negative 4. Negative 4 multiplied by negative 4. Then we are applying the negative sign to the result. We have negative of 16, because negative 4 multiplied by negative 4 is positive 16, and this negative sign takes its position right here. The answer is negative 16. We are demonstrating that the negative of a square is always negative. The cube of a number will have the same sign as a number that is being cubed. This is not difficult to see when the number being cubed is positive. We are saying that when we cube a number, the answer will have the same sign as the number that we have cubed. So if we cube a positive number, that's not difficult. Positive multiplied by positive will give a positive answer. Not difficult at all to see when the number is positive. If the number is negative, then we know that a negative multiplied by negative results in a positive, and we have another negative to multiply by, like in this particular case where we have negative 4 multiplied by negative 4 is positive 16. Then we will have another negative 4 to multiply it by. So 16 multiplied by negative 4, and the answer is negative 64. Therefore, the cube of a positive number is positive, and the cube of a negative number is negative. Negating the cube of a positive number is quick and simple. Since the cube of a positive number is positive, we will be applying a negative sign to a positive number. That will always give a negative result. So we are finding the negative of a cube. So we will cube the positive number and the negative sign is applied. We are talking in this particular case about the cube of a positive number. So we are cubing the positive number and we are taking the negative of the result. The cube of a positive number is positive. Then we take the negative of the result. The answer is negative 64, confirming by using a positive number that the negative of a cube will have a sign that is different from the number that we cubed. If we cube positive 4, the negative of positive 4 cubed is negative. So the sign will be the opposite of the number that was cubed. As we have seen before, the cube of a negative number is always negative. If we apply a negative sign to the cube of a negative number, then we will be applying a negative sign to a number that is already negative. This will give a positive answer. So we have the negative of the cube of negative 4. So cubing negative 4, we get negative 64 as we have right here. The negative of negative 64 is a positive 64. Summarizing, the square of a number is always positive, meaning the square of a positive number is positive and the square of a negative number is negative. The negative of a square is always negative because we are simply applying a negative sign to a square, and a square is always positive. So the negative of a square is always negative. The cube of a number will take the same sign as the number that was cubed. The cube of a positive number is always positive. The cube of a negative number is always negative. The negative of a cube will be of the opposite sign to the number that was cubed. Therefore, if we cube a negative number and take the negative of it, we will have negative multiplied by negative, and that will turn out to be positive. So, taking the negative of the cube of a negative number, the answer is positive. Also, if we have a positive number and we cube it, then we take the negative of that cube, that answer will be negative, because by taking the negative of the cube of a positive number, we will be taking the negative of a positive number, and that will always be negative. With all that was said and done, the difficulty expected because of recalling and determining the principles involved in manipulating powers and signs did not materialize in this problem. Probably the examiner intended that the candidates should expect that and make an unnecessary meal of a very simple situation. The constructs of the problem were not difficult to manipulate, but those explanations were thrown in for future references. In the Venn diagram, what does the shaded area represent? Notice that in the Venn diagram, the entire area is shaded with the exception of the set P. The complement of a set, say P, is defined as the set of all elements that are not in the set P. The set of all elements that are outside of P. The complement of P all of the elements that are not in P. Therefore, the shaded region represents the complement of P because it is the area that is outside of P that we have shaded right there, and the entire area. The complement of P is written like we have it right here. The correct answer is option A. If U, which is the universal set, is equal to the set 1, 3, 5, 6, 8, and A is equal to 3, 6, then the number of elements in A complement is, we are at complement again. The complement of a set A is called A complement, and it is written like we have it right here. It is the set of elements that are not in the set A. The complement of a set is usually defined relative to some predefined universal set. In this particular case, the universal set is given. Right here, the universal set is this one. We therefore need to determine the number of elements according to the requirements of the statement of the problem that are in the universal set but are not in the set A. We need to determine the number of elements, not the elements, the number of elements. There are 5 elements in U and 2 in A. The number of elements that are in U that are not in A is 3. The correct answer is therefore option B. The error that usually occurs with the greatest frequency in a situation like this is that candidates miss the statement that says the number of and just determine the elements. There should be no great danger of such misinterpretation because no option contains the elements of A complement. Furthermore, when the elements of a particular set is solicited, they are expected to be in brackets. The nature of the problem, which is a multiple choice, this problem is a multiple choice problem, has captured the error. The error is more prevalent in essay type problems. So when we generally have a problem, essay type, that requires that we determine the number of elements of a particular set, some students just write down the elements of the set. We do not have that danger here because in writing down the elements in a set, we usually write the elements enclosed in this same type of brackets. We do not have such an occurrence in the options. Therefore, that mistake could not have been made in this particular problem. Also, we do not have any option that contains the elements that are in the complement of A. Therefore, because of the fact that we have a multiple choice problem, the error that we would have generally made is captured by the fact that the problem is multiple choice, and we know that that error is more prevalent in essay type problems. Same problem, we may use a Venn diagram to assist in solving the problem. There we have our universal set, and A is inside of that universal set. When completing a Venn diagram, the elements of the set that is contained are inserted first. So the set that is contained in the Venn diagram, those elements are included first. There we have 3, there we have 6. Those are inserted first, and they are inside of the set A. the elements that are not in A will be included inside of the Venn diagram, but not inside of A. 1, 5, 8. Number of elements in A complement, that is what we need to determine. The number of elements in the Venn diagram that are outside of A is 3. There we have them, 1, 2, 3. It was not necessary to use a Venn diagram as we demonstrated in the first take at solving the problem. In an examination, time is of the essence. The shorter the time that we spend on a single problem, the better, if we can determine the correct answer. We do not know when a problem will require a bit more than the average time. Do not be afraid to solve a problem at sight. So if you can look at a problem and write down the answer, do not be afraid to do that. It is not every problem that is designed to consume 25 minutes. So in an examination, it is not every question that we have there is designed to take half of the entire time of the examination. We expect that some of them can be done in a short period of time. We do not write them off as being too easy to be true. We just take them at face value. If it is mathematics, there is no trick problem. All problems may be solved by strictly considering the information that is given. Easy problem, taking a few seconds. Not a trick problem if all of the information necessary in solving the problem is given. Which of the following sets is equivalent to the set A, B, C, D? If two sets A and B are equivalent, then there exists a one-to-one correspondence between the elements of A and B. All this requires is that the two sets have the same number of elements. Number of elements of A is equal to the number of elements of B. Those two sets are equivalent. Therefore, if we can identify the set in this particular case that has the same number of elements as the one in the statement of the problem, our work is done. Sets are equivalent. They have the same number of elements. The one that is equivalent to this one will have the same number of elements as this one. As soon as we have identified that set with the same number of elements as this one, our work is done. That's the one in option C. The correct answer is option C. If a set A is equivalent to a set B, we write, this is how we write it, with one part of an arrow and then the other part like that. Be careful to note that equivalence does not require that the elements of the two sets are the same, which of course is the requirement of equality. In the Venn diagram, the two circles represent set P and Q. If P equal factors of 6 and Q equal factors of 4, then the shaded region represents, what are factors of 6? Factors of 6 are numbers that can divide into 6 without leaving a remainder. The following set represents factors of 6. We have the factors of 6 right there. 1, 2, 3, and 6. All of those numbers can divide into 6 without leaving a remainder. Factors of 4 are numbers that can divide into 4 without leaving a remainder. The following set represents factors of 4. all of those numbers can divide into 4 without leaving a remainder. 1 is a factor of every number, and every number is a factor of itself. Why? Because factors are those numbers that can divide into, and of course any number can divide into itself, and 1 will be able to divide into any other number. So 1 is a factor of every number, and every number is a factor of itself. The shaded region represents the set of numbers that the two sets have in common. It is the intersection of the two sets called P intersection Q. The elements that are present in both sets are 1 and 2. The correct answer is option B. The answer in option D demonstrates the common mistake that candidates make. It is of mistaking factors for multiples. So try not to mistake factors for multiples in a problem. This is the common mistake that students make. When multiples are required, they work for factors. When factors are required, they work multiples. Multiples of 6 are numbers that 6 can divide into without leaving a remainder. The following set represents multiples of 6. 6, 12, 18, and the list will continue indefinitely. Multiples of 4 are numbers that 4 can divide into without leaving a remainder. The following set represents multiples of 4. 4, 8, 12, and the list will continue indefinitely. Every number is a multiple of itself and 1. That means every number is a multiple of 1, and every number is a multiple of itself. A student considering multiples would have considered intersection of the sets to be the common multiples of 6 and 4. Bearing in mind that sets of multiples represent infinite sets, the set of common multiples will also turn out to be an infinite set, as we have in option D. If $6 Trinidad and Tobago currency is equivalent to US $1, then $15 of Trinidad and Tobago currency in US dollars will turn out to be what? The alert candidate will be quick to see that 15 is 2.5 times 6. He will therefore choose option C in a matter of seconds. So we have 2.5, which is $2.50. We have the rate that's given here, and we have 6 to US 1. Then we have 15. If the candidate is alert and is on top of his digits, he will have no difficulty seeing that 6 divided into 15 is 2.5, and he will quickly write down 2.5 or $2.50 as the answer. Option C. In solving this problem, a table will be used as a guide. The values to be calculated must be consistent with those that indicate the rate of exchange in the first row of the table, and that is in terms of relative sizes. In solving the problem, a table will be used as a guide. The values to be calculated must be consistent with those that indicate the rate of exchange in the first row of the table, and we are talking about relative sizes. There we have the table. The table will now indicate the rate of exchange. That is the rate of exchange. We have the amount in Trinidad and Tobago currency, which is $15, but we do not have the US counterpart. According to the rate, the larger figure is on the Trinidad and Tobago side. Converting to US will require a smaller number. In order to achieve this, we divide by 6. According to what we have here, the larger number is on this side. The smaller number is on this side. The figure that we have is on the Trinidad and Tobago side. We imagine that the corresponding figure will be smaller. That is the one that will end up on the US side. How will we achieve a smaller number? The smaller number is achieved by dividing by 6. 15 divided by 6 is 2.5, so we have $2.50. We are talking about the consistency of the table. And the consistency that we are mentioning is of relative sizes. According to the rate, the larger figure is on this side. We have $6 greater than $1. If we are given Trinidad and Tobago currency to be converted to US currency, we will have to maintain that consistency with the number on the Trinidad and Tobago side being larger than the number on the US side. And we will get the smaller number by dividing by the figure that is inside of that rate. That is the use of the table, the consistency. We cannot be jumpy about this because the rate may be given in such a way that dividing will result in a larger number. That is when we are dividing by a fraction that is less than 1. We are being systematic, but we need to take a look at our answer, ensuring that consistency is maintained. So we cannot assume that because we want a smaller number that we divide. Because if we are actually dividing by a fraction that is less than 1, the answer will turn out to be larger. Therefore, although we are being systematic by using the table, being systematic does not guarantee correctness. While being systematic, we have to ensure that the requirements of being systematic are maintained. We will take another go at the problem. In another take on solving the problem, we may use ratios. We will also be systematic here, writing all US figures on one side and all Trinidad and Tobago figures on the other side. The rate of exchange will be placed in a ratio. So we have US side, Trinidad and Tobago side. The rate is US $1 to Trinidad and Tobago $6. That is consistently placed in the ratio also. We have the amount in Trinidad and Tobago currency. We do not have its equivalent in US currency. We will call its equivalent X and write it in another ratio with Trinidad and Tobago $15. So that X that we do not know, which is the US equivalent of 15 Trinidad and Tobago dollars, we will call that X. We will place it in a ratio and maintain the same consistency as we have in the ratios that are given already. X that we do not know is on the US side, and Trinidad and Tobago currency $15 will be placed on the Trinidad and Tobago side. There are many ways that equivalent ratios may be converted to equations. We will write the numbers in the second ratio as the numerators of equal fractions. the first numbers will be the denominators. This is so that the unknown may be in the numerator on the left hand side, making transposition, if necessary, and solution quite simple. So in taking that approach, transposition, if necessary, and also the rest of the solution will be quite simple if we do it like that. That is, if we write these numbers as the numerators of fractions that are equal, we will have x over 1 and 15 over 6. We are writing the x in the numerator because when the unknown is in the numerator of one of the fractions, transposition, if that is necessary, and the solution of the problem will be much simpler. So there we have it. X over 1 is equal to 15 over 6. Anything, x included, divided by 1 is equal to x. And 15 divided by 6 is equal to 2.5. So we have $2.50, and that is our correct answer.